What are smart contracts? Smart contracts are self-executing contracts with the terms directly written into code. Unlike traditional contracts that require third-party enforcement or intermediaries, smart contracts eliminate the need for middlemen. Smart contracts operate on the if-then principle. If a predefined condition is fulfilled, then a predetermined action is automatically executed. Smart contracts operate on blockchain technology, making them transparent, immutable, and trustless. In summary, smart contracts are self-executing agreements written in code that automatically perform actions when conditions are met, all without intermediaries. Smart contracts are powered by blockchain platforms, with Ethereum being the most widely used. Other platforms like Solana, Polkadot, and Cardano also support smart contract functionality. Smart contracts are written in specialized programming languages. Solidity is the most popular language for Ethereum, while platforms like Solana use Rust. These languages provide the functionality needed to define contract logic, manage state, and handle transactions. What makes smart contracts unique is their distributed execution. The code is stored and executed across all nodes in the blockchain network. This ensures there is no single point of failure and provides high availability. Every transaction in a smart contract must be verified through network consensus. This means multiple nodes must agree that the transaction is valid before it's added to the blockchain. This consensus approach ensures security and prevents fraudulent transactions. Smart contracts are highly secure and resistant to tampering. Once deployed, they're immutable and transparent, with their code visible on the blockchain. The redundant storage across thousands of nodes ensures reliability and censorship resistance. Smart contracts are revolutionizing numerous industries through automation, transparency, and increased efficiency. Let's explore how these self-executing contracts are transforming 6 key sectors. In finance, smart contracts enable automated lending protocols that remove middlemen and reduce costs. Insurance claims can be processed automatically when predefined conditions are met, such as flight delays or weather events. Decentralized exchanges use smart contracts to facilitate peer-to-peer trading without traditional intermediaries. In supply chain management, smart contracts enable transparent tracking of products from manufacturer to consumer. Each transfer along the supply chain is verified and recorded on the blockchain, creating an immutable history of the product's journey. Real estate transactions benefit from smart contracts through automated escrow services and streamlined property transfers. A smart contract can hold funds in escrow until all conditions are verified, then automatically transfer property titles and release payments. In healthcare, smart contracts enable secure sharing of patient data while maintaining privacy and control. Patients can grant specific permissions to different healthcare providers, maintaining control over who accesses their information. Smart contracts can transform voting systems by creating transparent and tamper-proof election processes. Each vote is cryptographically secured and verified, ensuring that the election results are accurate and publicly verifiable without revealing individual voters' choices. Smart contracts revolutionize intellectual property rights management through automated royalty distributions. When content is used, smart contracts automatically distribute payments to creators, ensuring fair compensation while simplifying the licensing process. Despite their potential, smart contracts face significant challenges. They're only as good as their code. Bugs or vulnerabilities can lead to substantial financial losses. A notable example was the DAO hack of 2016, where attackers exploited a recursive calling vulnerability. This resulted in the theft of approximately 3.6 million Ethereum, worth about $60 million at the time. Smart contracts lack flexibility once deployed. Their immutable nature, while a security feature, makes error correction extremely difficult. Legal enforceability remains uncertain in many jurisdictions. The legal status of smart contracts varies widely across different countries and regions. Smart contracts face significant scalability issues. During times of high activity, blockchain networks can become congested. This leads to high transaction costs, with gas fees spiking dramatically during peak network congestion. Smart contracts struggle with accessing off-chain data reliably. This is known as the oracle problem. Oracles provide external data to smart contracts, but they introduce potential points of failure and data reliability issues. These limitations represent significant challenges that must be addressed for smart contracts to reach their full potential. Oracles are specialized services that connect smart contracts to the world outside their blockchain. They serve as bridges between the isolated blockchain environment and external data sources. Smart contracts face a fundamental limitation. They cannot directly access external data. They exist in an isolated environment within the blockchain, separated from the outside world. This is where oracles come in. Oracles serve as trusted intermediaries that fetch external data and deliver it to smart contracts in a format they can understand and verify. Oracles can provide smart contracts with various types of external data. Financial data like cryptocurrency prices and exchange rates are among the most common. Weather data is also important, allowing contracts to access temperatures, rainfall amounts, and other meteorological information. Event-based data such as sports results, election outcomes, and transportation statuses enable smart contracts to execute based on real-world events. Finally, API responses and IoT sensor data create endless possibilities for smart contracts to interact with web services and physical devices. Here's an example of a smart contract that uses Oracle data to execute a trade when the Ethereum price reaches a certain threshold. Projects like Chainlink have revolutionized oracles by creating decentralized oracle networks. Unlike single, centralized data sources that represent a point of failure, decentralized oracle networks aggregate data from multiple sources. These networks offer several important advantages. They pull data from multiple independent sources and use consensus mechanisms to validate information before delivering it to smart contracts. This decentralized approach makes Oracle data feeds resistant to manipulation and single points of failure. Node operators also have economic incentives to provide accurate data, further enhancing reliability. Despite their benefits, oracles present significant security considerations. They can potentially become vulnerabilities in otherwise secure smart contract systems. Key challenges include potential manipulation of single data sources, compromised Oracle nodes, network downtime that could halt contract execution, and general reliability issues with data sources. To mitigate these risks, developers should use decentralized Oracle networks whenever possible, implement multiple layers of data verification, and set minimum response requirements before smart contracts accept external data. In conclusion, oracles are essential components that enable smart contracts to interact with the real world, but they must be implemented with security as a primary consideration. Smart contract development requires specialized knowledge of blockchain architecture and programming languages like Solidity. Let's explore the development and auditing process. The development process begins with requirements gathering and understanding the blockchain architecture. Developers then design and code the smart contract, followed by local testing. Due to the immutable nature of smart contracts and the often substantial value they control, rigorous testing and auditing are essential. Professional audit firms specialize in reviewing smart contract code for vulnerabilities like reentrancy attacks, integer overflows, and front-running. The auditing process involves manual code review, automated scanning tools, formal verification, security analysis, and a final report highlighting issues and recommendations. Best practices for smart contract development include extensive testing, formal verification methods, thorough code documentation, implementing upgrade mechanisms for critical fixes, and undergoing security audits. The development and auditing process should be integrated, with security considerations built into every step of development rather than added as an afterthought. By following rigorous development practices and undergoing professional audits, developers can minimize the risk of costly vulnerabilities in their smart contracts. The future of smart contracts is evolving rapidly, with several key innovations pushing the technology forward. Layer 2 scaling solutions address smart contracts' transaction costs and speed limitations by processing transactions off the main blockchain. Solutions like optimistic rollups and ZK rollups can handle thousands of transactions per second while maintaining security. Cross-chain interoperability protocols are enabling smart contracts to work seamlessly across different blockchains. Projects like Polkadot, Cosmos, and Chainlink are creating protocols that allow different blockchains to communicate and share data, expanding the reach and utility of smart contracts. Privacy-preserving technologies are being developed to enable confidential smart contract transactions while still maintaining verification. Zero-knowledge proofs, trusted execution environments, and secure multi-party computation allow for private data and computations while still providing the transparency and trust that blockchains offer. As regulatory frameworks mature and adoption increases, smart contracts will likely become fundamental components of digital infrastructure across industries. Financial institutions are already implementing smart contract solutions, while sectors like supply chain, healthcare, and government services are quickly following. By 2030, we expect standardized regulatory frameworks and widespread adoption across most major industries. In the coming decade, smart contracts will evolve from experimental technology to critical infrastructure, powering everything from financial systems to digital identity, IoT networks, and government services. The future of smart contracts isn't just about blockchain technology. It's about reimagining how digital systems interact in a trustless, programmable world. Looking to get started with smart contracts? Let's explore the available resources. For developers, Remix IDE offers a browser-based environment for writing and testing Ethereum smart contracts. This platform requires no installation and provides a complete suite of development tools. Educational resources abound for those looking to learn. Ethereum.org provides official documentation, Solidity Docs offer language references, and platforms like Coursera feature structured courses from blockchain experts. Non-developers can experience smart contracts through user-friendly platforms. Polygon and Binance Smart Chain offer lower-cost environments to interact with existing applications without any coding knowledge. These resources are interconnected. What you learn in educational platforms can be applied in development environments, and the applications built by developers become accessible to non-technical users. To begin your smart contract journey, first choose your path as a developer, learner, or user. Start with beginner-friendly resources and always test in low-cost environments before deploying to mainnet. The world of smart contracts is interconnected and evolving. By starting with these resources, you'll be well on your way to participating in this transformative technology.